Oh, can you hear me?
Yeah.
Can you see the screen? First of all, thanks for having me here, and thanks for the invitation. I really appreciate it. My name is Zipeng Ling, and again, I want to briefly introduce myself. I'm an upcoming MSc thesis-based student of University of Alberta, majoring in computing science. I spent 1 year as a gap year working as Bosch as an NLP research intern. So during my internship, I mainly do like deep research related work, like the company itself has very confidential documents. We want to make use of them in the RAG flow, in the RAG system of the deep research system, to like somehow generate detailed and confidential reports for our internal employees' usage. So that's somehow a specialized deep research system, also from compared with the public available ones. And also, I will be working in Alberta Machine Intelligence Institute as a student researcher because this like program is like somehow collaborated with University of Alberta. So that's a brief introduction about me. So I like to present this paper. It's submitted to the May submission cycle, and it got like 3.67 overall assessment. Like it's 4, 3.5, 3.5. Um, Meta review is not released yet, but somehow it's a pretty high score. Maybe it's suitable for a presentation. The research area is NLP and symbolic reasoning, which is not very like a competitive track among all ARR regions tracks compared to like resources and evaluation. So I like to briefly introduce my paper, the pipeline of my paper. So we initially talk about our motivation, and we carry out a very interesting empirical study. And based on the problem exposed by the empirical study, we propose a methodology to mitigate the problem. We carry out detailed experiments, evaluations, and based on the methodology itself and empirical study, we carry out further detailed experiments, and we reach out our conclusions and contributions. So for the motivation part, we can tell that, as you can see, if we input reasoning samples into LLMs, ideally it thinks step by step correctly and reaches the final correct answer. Is the ideal way. But now, in practical, LLMs like just reach maybe step one correctly and all other steps wrongly and finally achieve the correct answer. This might be the situation. So um this is further proved by a position paper. Like the essence of reinforcement learning may be just for LLMs to find a tricky way to reach the correct answer rather than really help them really comprehend how to reason. So this part is pointed out in the NeurIPS 2025 paper, in a position paper. So we systematically categorize all the flaws and problems in the reasoning. It's mainly like two parts. So part one, we can see that. Sorry for my. Part one, we can see that for the pink one, step internal flaws like logical errors and hallucinations and extra, like the content of these steps. And the second part is stepwise flaws. So there may be overthinking for redundant steps or like underthinking for missing steps. So one is from the content, one is from the structure. So there may be various of reasoning flaws contained within the samples, and LMs just maybe somehow find a tricky way to like across all the wrong steps and reach a correct answer. So that's the problem background. Correct label prediction is related to, but not fully determined by whether the reasoning steps are correct. So To solve this problem, there are previous methods focused on similar fields, essence, but they fell short on several parts. So one is like the paper accepted by iClear Conference Logical Awards. It only studies logical reasoning, but it totally omits mathematical reasoning, despite it's very popular in reasoning field. So it's like the domain is very, very narrow. For the second part is like the motivation we want to address the most, like the flaw type coverage. Existing methods assume a single flaw type holds for all traces. Like they deal with the problem. This paper deal with the problem. Consider all the samples suffer from all underthinking, like step missing, like this part. Like this part, we can see that underthinking missing steps. And for the other paper, PNS, also accepted by NURBS, it suggests that all reasoning traces suffer from overthinking, and they just propose the methodology accordingly. We can tell that this really feels on practice, because if we get like 70 out of 100 scores in an exam, how can we tell that all the problems we make like are result from the same questions? Maybe we do varieties of mistakes, and finally we got like 70 out of 100 in an exam, right? So we argue that we should not prescribe flaw types for hold for all traces. So the problems can vary from sample to sample, and eventually they are mixed together, just like this. Just like the problem background, there are varieties of flaw types: step internal flaws, stepwise flaws. Their sample A has A flaws, sample B has B flaws. So eventually, the samples with different kinds of flaws, they are mixed together. So we consider the problem to be like this, but we do not prescribe the one single flaw type holds for all traces. So that's a problem of previous methods. So before we dive into how problems should be mitigated, we just did a very, very simple but interesting study. If LM reasoning arises from uncertainty about the correct answer, the simplest fix would be provide the answer directly and merely require the model to justify the given answer. So if we give the final ground truth answer, can this help improve LM reasoning ability? We ask a very, very simple and interesting question. We don't know, right? We carry out experiments in as an empirical study. So for the LM reasoning ability, it has two aspects. LM as a step-by-step verifier. It's like if we give for giving problem, if we say the answer is 5, and LM should be as a step-by-step verifier to check whether each step is correctly operated, then finally reach the correct answer 5. This is as a step-by-step verifier to verify the previously annotated problems. It's the second part. Um, LLMs themselves may generate reasoning traces given the correct answer, and we do evaluations on those generated reasoning traces. So these are two parts. One is as a verifier to check annotated problematic reasoning traces. One is generates reasoning traces themselves and use reasoning benchmarks to help evaluate the quality of these traces. So we do all these two experiments together. As you can see, for the first part, step-by-step verification, PRM bench, annotated wrong steps. There are annotated wrong steps without answer. We input LM, and with answer, we input LM for the two separate settings, and we compare predictions, predicted wrong steps. The effects are similar. Yeah, and annotated their annotated evaluation steps were like ground truth labels for comparisons. We find out that there are minor differences, so we can judge this from the horizontal line. uh,
Hi,
without answer.
sorry, Sean has a question. Sean, do you want to unmute and ask? Does this answer your question in any way?
Sorry.
Oh, yeah, sort of. Like earlier on, there was like the illustration that sometimes the model will, what's it called? The model will like not follow a correct reasoning path within the knowledge graph, right? And like,
Yeah.
um, basically, like the main intuition is to correct this, to like prevent it from like having this hallucination path, right?
Sorry. I think I may not hear it very clear. So there are hallucinations.
Yeah. And then like the motivation is to like reduce these.
So the motivation is to like there are various kind of flaws. Like there are logical. We can see that from these two lines. There are logical errors. There are hallucinations, and there are overthinking and underthinking problems. But this is proved. This is indirectly proved in a positional paper here. But later, um, the existing methods assumes one single flaw type holds for all traces, so you can find the two related articles here. So, so sorry, I may not hear it very clearly. What is your question?
Like that's the motivation for flaws of previous methods, right?
That's a motivation for our proposed methods, but we have not released our proposed methods yet. We just proved that there are problems, and the previous method fell short on identifying them, fell short on they prescribe a wrong background. So maybe could you type your questions briefly in the comment section below?
No, it's okay. I will just like watch the rest of your talk.
Oh,
Thank
okay.
you.
So let me see. Um, we discovered this problem, and here we do a empirical study, and we did not yet go directly to the methodology problem part. So we want to make our work little bit like in depth in this part, like regarding analyzing. So so we now know that there are like various reasoning flaws within each from sample to sample, and like the problems with different flaws they are mixed together. That's key point we can summarize. And before proposing a problem mitigation method, we ask very simple questions. If LLM reasoning arises from the uncertainty about the correct answer, if so, the simplest fix would be provide the answer directly to and merely require the model to justify the given answer. So if so we did this experiments, we want to explore this research questions in two dimensions when LM as a step-by-step verifier to verify annotated wrong problems, or they generate reasoning traces themselves, and for benchmarks to evaluate whether given the correct answer can help improve the reasoning traces they generated. So these are like two dimensions of reasoning, right? So we carry out experiments separately in two settings, and for each setting we have with answer and without answer setting. So so first of all, step-by-step verification. There are annotated reasoning traces with wrong steps. We input them, we contain them without answer and with answer. We carry out the experiments separately and input LMs, and we find out LM prediction are exactly similar, very 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 similar, and finally compare with the annotated wrong traces. We find out that offering correct answer does not help improve LM's reasoning ability as a step-by-step verifier because their predicted wrong steps are exactly pretty the same. So this is the setting one. So for setting two, um, for input questions, we without answer, that's one setting, and for input questions with answer is another setting. We test them separately. Based on two settings, we generate reasoning traces. They are mostly similar. We do this evaluation based on like Robota and Set and Spurt to like based on their embedding to help classify their labels. So it's like a traditional NLP test to do MLP projection. So we discovered that all the reasoning traces LMs generated, their embeddings can be projected to mostly the same label. So they are mostly minor differences. So we can conclude that in most settings, offering the correct answer does not improve LM reasoning ability in either dimension. When LM serves as a step-by-step verifier, or when LMs generate reasoning traces themselves and for reasoning benchmarks to evaluate, we can see the significant test. So we can see that. Oh, it should be O for mini. Sorry, I should clarify this. Um, so for these chart, we can see that only some settings for some specific models, the influence turned out to be explicit, whether like you include the answer or you did not include the answer makes a like a explicit influences to the results. Like you can see that these two are very explicit. There are no explicit correlation at all. Like for there's only one exceptional thing is like for all tested models they show very unified and strong correlation when you add answer or you did not add answer in this sub data set. So we consider this is because the label biases. So for this sub data set, we consider that we discover that most LMs output like one specific label, but if we offer like the correct label, it turns out to be like the LM conform to the given label, and they just it's just largely changed their output distribution. So this may be a biased source as well. So only on this sub data set, offering the answer and doesn't offer the answer makes an explicit influence on LM reasonability. Others are like very like some partially correlated. So based on such an empirical study, we can conclude that in general, in most settings, providing the correct answer does not improve LM reasoning ability in two dimensions when LM serves as a step-by-step verifier, or when LMs generate the reasoning traces themselves and for reasoning benchmarks to evaluate this. In either dimensions, providing correct answer does not necessarily improve reasoning ability. Also, we can conclude that LM reasoning flaws cannot be solved by simply providing the correct answer. That's correct, right? If the flaws are still there, it cannot improve the correct answer prediction. Offering the correct answer for LM to merely justify it cannot help improve reasoning. So we conclude that a unified mitigation framework is necessary. So it echoes the previously our statement that you there are all kinds of flawed mistakes problems in reasoning, and they just somehow maybe achieve the correct answer accidentally. And if we give them the correct answer for LMs to justify it, there are still reasoning problems, and their reasonability is not improved in most settings at all. Like also echo with this part. Each method assumes a single floor type is for all traces, but we argue that no, they can make mistakes from sample to sample, and they can make various mistakes that cannot be assumed before. So based on these key takeaways, we propose our problem mitigation. So the principle of our problem mitigation is to roll out multiple reasoning traces and at a very high temperature. So the reasoning traces are diversified, but their the consensus part they share are kept, and the outlier parts they share are filtered out. So let me briefly introduce it first. We roll out multiple reasoning traces in advance at a very high temperature. We propose TF-IDF. Uh, so do I need to like a brief catch up with TF-IDF because it's like a very common concept in RAG. It's like term frequency inverse doc frequency is like you have like term frequency in doc A, but those like those frequency are very low in other docs. So you can tell that the terms in A help really shape the. So do I really need to do like a TF-IDF explanation? I don't think so. So based on So TF-IDF is to help identify the important words in the docs, in the rack systems. Hereby, we use TF-IDF to identify the important words in multiple reasoning traces. So for these reasoning traces, we calculate the term frequency within them and compare the inverse doc frequency with other reasoning traces, so we can tell that some specific nouns, some specific words are very important. Given such idea, we save the consensus and similar steps within the all rolled multiple traces and filter the outlier traces which do not have those steps. I will explain this clearly later. And we do a reasoning knowledge graph construction, and we filter the outlier nodes and edges, and we do a topological traces generation. So let me get this into details. So our mod our methodology has three parts. We roll out key traces from I to K. We roll out key traces and save them, and based on all the key traces, we apply TF-IDF, term frequency inverse doc frequency, and hereby we call it like term frequency inverse reasoning frequency, like to help identify, you know, the steps with important terms are like kept, and the steps with outlier steps or steps they do not share the consensus like words, they should be filtered out. Like and for those steps, we apply a z-score filtering, like those are filtered out. For the second part, we do we use LM to construct the reasoning knowledge graph based on all those reasoning traces that after the step filtering. You can see from line 7 to 8. Steps to nodes and logical relations to ages is a very simple, commonly used way to construct graphs. And for line 9, we reiteratively do like a age sum. For line 10, we use LM reported confidence and the jacket similarity between consecutive ages as a weighted sum to calculate the age weight as shown in line 10. LM reported confidence and node jacket similarity. Based on the weighted age sum, we filter out all the ages that below the specific threshold, and we filter out all the nodes that has 0 in degree and 0 out degree. And that is like, you know, the nodes do not contain any edges, whether it's an in age and or goes in age and goes out age. So we filter out outlier nodes and edges, and we do a graph aggregation based on the all we roll out traces, a reasoning knowledge graph. Like for all every trace we construct a reasoning knowledge graph, and here line 12 we aggregate all of them to a one giant graph. So the so later we do a like topological traces generation based on the logical graph. We generate the final reasoning trace. So let me explain this in details. So our methodology contains three parts. So part one is multi-traces generation and step filtering. Input the questions and we roll out key traces, like they're literally key traces, key reasoning traces, and we apply TF IRF, the variant from TF IDF to compare the specific words within steps. So steps do not contain the consensus words are filtered out by this school filtering. So sorry. So sometimes like this part, sometimes they're filtered out. Sometimes they they do not contain this step at all. We can tell that generating generating reasoning traces at a very high temperature makes these diversified, and we want to just keep all of them. No, keeps them a consensus part of them. Okay, so for step filtering, later we go on. We use LMs to construct graph, like for this part. For reasoning for each filtered reasoning steps, we use LM to construct graph, reasoning knowledge graph with different nodes and ages, and then we do a like for later we do a Jacket similarity for ages and reported confidence for ages to determine whether ages are kept uh, and if ages are filtered and the nodes without with 0 in degree and 0 out degree are filtered as well. So we do a filtering, we do an aggregation, we do aggregation for the final reasoning knowledge graph, and based on the final reasoning knowledge graph, we propose a topological guided trace synthesis, like we use LM to synthesize the final reasoning trace, and we do multi-facet post evaluations on both label prediction and accuracy. You can see that on both label prediction accuracy and reasoning traces quality evaluation. For our work compared with previous work, you can see that there are we listed two examples for comparisons. So for this part, self-aggregation is like LM directly as a judge to aggregate the different parts of reasoning traces and to a final one which can induce biases. Yeah, and that's very unstable. For later MGRS, they use LM to grade all those traces and select the reasoning trace with the highest score directly. So this is also, I think they are kind of the same because they are just like use LMs which can post randomness and uncertainty into these processes. Yeah, so both of their methods we think they have flaws. For the experimental results, we do label predictions. These are all training free baselines. Our experiments achieves mostly the highest or second highest results, and in both accuracy and F1 score. But there's a problem. Like we can see that for average steps, our method does not help produce the least average steps. So these steps are a little bit too much, and we believe this can be a drawback of it. But we choose the the best or second best label prediction accuracy in different benchmarks evaluation, in both like logical reasoning and in both and mathematical reasoning benchmarks. So yeah, beyond the label prediction, we also propose reasoning traces evaluation. Um, we use the previously proposed published re- reasoning benchmark evaluations, and we just achieved the much higher results. Um, yeah. So we also do a very here's a very interesting part. Do the ablation study to filter out each part of our components and results. We use the jacket similarity in our methods. Like it was like how to say that? It's a keyword matching, right? The the consecutive steps share the similar words are considered to share the similar higher similarity. So we replace this with dense retrieval. Like we use a text embedding model, like the we use the text embedding model to compute the cosine similarity of consecutive steps, and we find out that this doesn't work very well, and also like there is minor accuracy drop, and there are also like additional cost because we use like model API to compute the cosine similarity. This cost much higher cost compared with like Jekyll similarity, which can calculate it by formal verifications. So it's cheaper and it's more stable and it offers higher accuracy. So that's why we use Jekyll similarity. So for the reasoning knowledge graph construction, there we can see the shadow part. When reasoning knowledge graph, the agents knows the number increases, so the accuracy itself is positively correlated with the sizes of RKG reasoning knowledge graph, and later it fluctuates around the highest accuracy or like it converges to the highest accuracy. So the RKG we constructed, reasoning knowledge graph we constructed, helps improve the label prediction accuracy, and later it's the accuracy converged. Also, we do a noise analysis based on the graph construction. So we select three models like GPT over mini, GPT 5.4 nano, and GPT 5.4. All those three models perform exactly the similar. So we believe the LM for graph construction does not induces much noise because the models for like for different tiers, different parameter sizes are performing exactly similar. So finally, we reach out the conclusion and contributions. We propose a benchmark evaluate empirical study. Providing the correct answer in most settings does not yield consistent improvement in reasonability in two dimensions when LMs as a step-by-step verifier or when LMs generate reasoning traces themselves, and for a reasoning benchmarks to evaluate this in two dimensions, there are no consistent improvement in most settings. Second part, we can tell that the the reasoning problems does not arise from the answer uncertainty, but from the reasoning traces structure. So we propose craft. So we propose our methodology, a unified framework that mitigates different flaws types and yielding consistent label prediction accuracy gains. And for the third part, we do a post-process reasoning traces evaluation. Uh, we not The post-process reasoning traces not only achieves like higher label prediction accuracy, they also achieves higher quality under fine-grained reasoning benchmark evaluation. So that's most of the core parts of my paper. Thanks for listening.
Yeah, thank you, Zipeng, for your talk. And yeah, I think we have managed some time for Q&A. And if you have any questions, just raise your hand. Yeah, and I can go first. Yeah, I have one question. So for
Yeah.
the can you go back to the slide where you show the frame like the framework like about the logic? So like 2 point. Yeah. So craft about craft. So you show that like the graph with different nodes and edges like it's like sort of like I'm a really visual person, so I see it's like is that linear or like you have like how did you construct this kind of logics with nodes and edges, or it's like how it's different from the literature?
Oh, so our novelty doesn't lies with graph construction because like LM
Mhm.
construct graph, it is considered to be an imperfect way, and they can cause noises. And also you can see that in the last part we do a noise analysis on graph construction by applying different tiers of models to eliminate the noise analysis. It eliminates the influence of noises.
Mhm.
Um, so for this part, we just use like a system prompt for LMs to construct the nodes. Like as we can see from the explanation here, build RKG, step as nodes, and logical correlations with edges. So we just tell LMs to do this. So yeah,
Okay, so is
this.
that linear or it's like a graph? It's like a chain of like as shown in the
Oh
graph.
yeah, it's linear. It's linear. So yeah.
Okay. Okay, yeah, that might make sense for LM to do this, but yeah. Okay, and I have another question about the correlations. You show the like the very last slides when you have shown that the yeah, so it's saying that between different model like with different model size like oh for mini and then nano like it's really similar. Um and as from the like O four mini and then from the B like a graph B O four mini, it's like a little bit different, like a really like small difference between like 0.99 and 0.98. Do you think that's like a really because I'm not really into this field, so but what I'm thinking is like is it um I would say it's like the normal thing to have this kind of correlations, or it's like less all obvious, like less common to have this kind of 0.98 and 0.99. Like this is really extremely close. Like I mean, it's like statistically because I'm from stats, so it's like almost like impossible for stats person. Like if I see like this is kind of too close to one.
So
Yeah.
so initially when we use like LM to construct graphs, there must be like different kind of reviewers raising concerns, including the reviewers reviewing my papers. Um, they have concerns about graph constructions, and this part is to help eliminate their worries. So
Oh,
so uh, what you mean by too close and like is there two
like
unrelated?
I mean, is it just showing that the this is like this kind of graph recently is really extremely stable between different
Yeah.
models? It's almost the same between different scalings of different models. Have you tried different models just except for like GPT 5.4? I think like all like and there are also new models like probably Cloud
uh,
or yeah. Have you thought
uh
about anything like that?
yeah, we did not.
That's fine.
But there should be one, but I feel like this does not like induce much differences because like
Mm-hmm.
models with hundreds of times of parameter sizes gaps, and they are producing exactly similar results based on the same prompt. So we're not very worried about that. So
Okay. Okay.
yeah,
Yeah. Thank you so much.
thank you.
Yeah. And does anyone else have any questions?
That's really good questions if the reviewer brought it up. Qifeng, can you read the questions from Shang?
Sorry.
So, like Sean has another question earlier. So it was what he said, like earlier there was a point on the model that doesn't follow a valid path in its reasoning, why that might be.
Okay. So you mean like based on our methodology, there may be like false elements aggregation and further induces biases, right?
Yeah, sorry, I'm not exactly sure about what Sean asked, but yeah.
Based on the experiments and during our bottle session, some reviewers really raised this question, and we elaborated from two parts. So first of all, like based on our empirical findings, the size of reasoning knowledge graph is positively correlated with the label prediction accuracy. So when the reasoning knowledge graph ages and nodes increases, the label prediction accuracy first increases, then fluctuating around the highest accuracy. So based on this empirical finding, we can tell that with more information available, with a larger reasoning knowledge graph available, the accuracy can achieve higher than it like converges. So this is the first part. This this is an empirical finding reflecting back on this. The second part is that, let me see. Based on the accuracy gain, we can tell that, you know, we reach our conclusion. We test, like here, the full benchmark we used were like they have different difficulty levels, but for all benchmarks, like they are whether they're easy or hard, they all offers like accuracy gain here. So we conclude an empirical finding. So even though the reasoning flows can be various and complex to capture, and they can be vary from sample to sample, they're the LMs still generate most of the steps correctly. So this is another empirical findings. Otherwise, the the framework will not work at all. So yeah, there are two empirical findings. Thanks. One is the reasoning knowledge graph size again is positively correlated with the accuracy. The other is like for the benchmarks, whether they are difficult or hard, easy, they're all like offering accuracy gains. So generate most of the steps correctly, and that's two empirical findings. So help prove that like the wrong elements aggregation can be somehow minor. Yeah. Yeah.
Okay, thank you so much. Yeah, yeah, I think that sort of solves part of Sean's questions. Yeah, and does anyone else have any questions? Okay. Yeah, and thank you so much, Zipeng. I think Sean will contact you later about his questions about, and then he will watch the videos we posted. Thank you so much for your presentation.
Thank you so
See you later.
much.
Yeah.
All the
Uh,
best. Thank you.
thank you, and thanks for having me here. I really appreciate